Buonasera, c'est le seul mot que je connaisse en italien.
Good evening. That's about the only thing I can say in Italian. Buonasera. Please excuse me, I can't speak Italian, but I'm extremely pleased to be here in Turin with you today because I lived in Turin for 10 days many years ago to write a book on Galileo. And so I am well acquainted with the city center, with the mountains surrounding it. The issue I would like to deal with today is focused on the pre-Big Bang. The question is, what should we say on physicists, and what would we say if, say, we were involved in Newton's equations on mechanics or gravitation, and if we could ask the equations themselves, what is time? What would these equations answer? Would they say the same thing as we say, for example, in our usual language? And it is this type of questions which I'm going to raise for the equation of cosmology, that is to say, the science of the universe. So I am going to ask myself about the origin of the universe, wondering whether the equations say the same thing as we say about the Big Bang. So there is a question which I have to start with, and it is the question on the link between... Oh, this is not a French keyboard. I have to learn... Right, this... what is the link between an object, a thing, and its origin? As you know, in the 20th century, we understood the origin of many things in the universe. For example, the origin of atoms. We understood how atoms were formed in the course of the history of the universe. For instance, we know that light atoms were formed in the first instance of the universe, and the heavier atoms, which go from lithium to iron, are the ones which were formed in the stars thanks to nuclear reactions. And the even heavier ones, which go from iron to uranium, were formed in the explosion of dying stars, and clearly they were the result of this, and this forms all the elements between iron and uranium. So we understand this, seeing the nuclear reaction between proton and neutron, which connect all and create all the chemical elements as we know them. We therefore know and understand that to understand the origin of something in physics means that you describe all the physical phenomena that make it possible to have the emergence of this which we're talking about, of what we're talking about. So, to an extent, in physics, the word origin means conclusion, or at least attainment, achieving something. In other words, the origin is the number of things that happened, that took place, and that make it possible for the object of our description to appear, the one we're talking about, the origin. So the origin of things is a part of the things. Protons and neutrons are part of the nucleus, they are the origin of. And the question I would like to raise this evening is, when you refer or apply this to the universe itself, can one think that one is describing the origin of the universe? Because if, for example, one were to refer this to the origin of atoms, to describe the origin of the universe means describing the series of processes which led to the origin of the universe, which underlying suggests that it was something before the universe. And if there was something before the universe, it means that what we're talking about wasn't the original origin, but the fact that the universe is the achievement of the process which started before the beginning of the universe itself. So to answer this question, one has to talk a bit about cosmology in the 20th century. As you well know, it's Galileo that invented the idea of the universe, that the idea of the fact that the world is formed of one type of matter, which is managed or ruled by some universal laws, and that there are laws that are the same in all parts of the universe or of space and at all moments of time. But up to Einstein, universe was not in itself a physical object. Universe was the envelope which contained all the physical objects, galaxies, stars, etc., etc. And Einstein, who is the first one on the left, you probably recognize them, 1915, so it'll be 100 years soon, spoke about a new theory of gravitation, which is called the theory of general relativity. And in the framework of this theory, gravitation is not simply a force amongst objects, it is a deformation of the structure of time and space. And it is a sort of conceptual revolution, which is also a revolution in that it is the first time in history that we have a formal theory that makes it possible to identify the universe itself as an object. According to the theory of Einstein, the universe has global properties which are not necessarily the same as the local ones. For example, the curve of the universe pertains or is relevant to the universe, but not necessarily to the object it contains. And therefore, the universe becomes a physical object in itself. And we can therefore study the history of such object. There are two other people who are very important in this. Up above there is the Abbé Lemaitre, who was in Belgium, and he was a canon there, and who theorized cosmology, and who was able to prove that the solution of Einstein's equations corresponded to an expanding universe. And he developed a theory which was called the theory of the primitive atom in 1922, with the idea that in the beginning there was a large nucleus of atoms with protons and atoms which exploded and which created space and time and the expanding universe. Then there was a Russian physicist, Freeman, did roughly the one below him. In 1926, I think he published more or less the same sort of work, but his were considered purely theory, without any practical implication, and without any reference to experiments. And then there's a fourth one, an American, Edwin Hubble, who was also a boxer in the States. And at night he made observations thanks to a very powerful telescope which he had, which is the Wilson Mountain telescope, the Mount Wilson one. And he observed the movement of what were then called nebulae and now called galaxies. And he noticed that the relative speed of galaxies was greater the greater the distance between the galaxies. So the greater the distance, the greater the speed. So their relative speed was bigger. Hubble interpreted this interpreted this as the fact that galaxies were progressively escaping from the universe. But when we interpret this on the basis of Einstein's equations, that is to say the relativity ones, the interpretation of the observations is modified. Instead of considering that galaxies move in space, one should consider that galaxies are immobile in space, but that the space which is in between them dilates. In other words, there is an expanding universe which is not to do with the position of the galaxies, but it is the dilation of the space which contains the galaxies. And it is that we call the expansion of the universe. And this implies that if you're able to look at the universe in the past, in the distant past, you will see a universe which is smaller and smaller, denser, and also hotter. And this is what the the fifth physicist, which I've shown here, George Gamow, who was Russian, and he understood that in the past the universe was not only smaller, denser, but also warmer, hotter. And in 1949, We then developed a model of the universe where, thanks to Einstein's equations, we were able to climb back into time, calculate the density, the temperature in the universe, and also we obtained this representation. That is to say, up above it's today's universe, but when you go back into the past, you have a denser universe, a hotter universe, and the calculations then you end by reaching a point which is physics is called a singularity, and which is associated with zero time, with a zero instant, and which in 1949 was named the Big Bang. This Big Bang is the original explosion which created all the things that exist, space, time, energy, and rays. And since we belong to a culture that promotes the idea that the universe was created, there is a sort of consistency between the Big Bang and the creation, fiat lux. They created a conflict or competition between the scientific discourse and the religious discourse. Currently, we still speak about the Big Bang in this way, and we have the idea that it is an explosion that created the universe. What I'm going to show you is that since 1950, cosmology has progressed, and that this way of telling the story of the primeval universe must be reorganized. Because since 1950, we have made a lot of discoveries which have therefore modified the scientific discourse. The reason why this must be corrected is due to the fact that in the universe you don't just have gravitation, there are other very important forces, for example electromagnetic forces, which you're well aware of, and there are also two nuclear interactions, one which is called the weak nuclear interaction, which is responsible for beta radioactivity, and the other one is called the strong one, which is within the nucleus of the atom is responsible of the relationship between neutrons and protons, and this is not included in the gravitation. In Einstein's equation, which only considers gravitation, which means that when you go back into the past, on the basis of Einstein's equation, you can do some calculations, you can perform them, which are mathematically correct but physically erroneous because they do not describe the physical phenomena which the particles experience at very high temperatures. I believe that you probably have heard CERN and the Hadron Collider, which exists in Geneva, and you accelerate the protons so that they have the same kinetic energy as a mosquito in flight, which is a lot of energy, which is a lot in some respects, but it is certainly not enough if we consider the type of energy that the particles had in the past. Initially, they had the same sort of energy as a train, an energy which is much higher than the one which we can reproduce in a lab. In these conditions, particles undergo the four forces: gravitation, electromagnetic forces, and nuclear ones, which are not described by Einstein's equation. Therefore, Einstein's equations, as from a given moment, become false in physics but true in maths, while remaining correct in maths. There is a moment here where Einstein's equations, I was saying, are falsified, and the moment after which they become falsified or no longer hold true, roughly here, it corresponds to what is called Planck's wall. Planck was a physicist, a German physicist, who invented Planck's, or discovered Planck's constant, which makes it possible to calculate the physical conditions whereby Einstein's equation no longer holds. So what one can say is that we are able to describe the history which goes from Planck's to the present day, and we know that history lasted 13.7 billion years. The question is, what happened before that? And to know that, we have to have a theory which is able to describe the 4 fundamental equations at the same time. Here you can see a slightly more modern representation. Here, 13.7 billion years. And here you have a very important phase which corresponds to light. That is to say, at the beginning of the university, the density of the matter was so strong, was so high, that light was not able to transmit. Every time a photon, that is to say, a proton which carries light, advances in space, it entered in contact with the matter, which deviated it, which means that light was not able to be transmitted. But the temperature has now become much lower. The first atoms were formed, and the light no longer interacts with atoms. So as from that moment, light can freely circulate at that. It was 4,000 degrees, and currently the temperature of that light is about 3 Kelvin. And it is that light that we observe thanks to satellites. It is what we would call the backdrop or the fundus. The satellite is going to give very interesting results in the next few days, and the information is going to tell us what happened before that phase. However, astrophysicists are unable to see objects which are older than the moment in which light appeared, because such objects do not emit light. Astrophysicists can only read into light. So, to know what happened there before light, you have to have a collision of particles at very high energy, and thanks to such collision, you can recreate in a very small space for a very short time the physical conditions which you had at that time. And since we believe that the laws of physics have not changed, if we recreate in the present the physical conditions of the past, we will see the physical conditions that happened at that time reoccur. But as I said earlier, we can't go before the situation where the energy of particle was the same as the energy of a mosquito in flight. So currently we are limited. We are unable to go back in time as we would, far back in time as we would like to be. So to go back in time, you must use equations, you must use calculations. And to have these calculations, you have to have a physical theory which is able to describe at the same time the 4 interactions which elementary particles undergo. And I repeat, gravity, electromagnetic forces, and nuclear forces. You see that in physics there is a sort of separation. Gravity is alone and is expressed by Einstein, which is the theory of general relativity. And the other 3 forces are described within another conceptual framework, which is called quantum physics. And quantum physics and general relativity are based on completely different principles, simply because the space is not the same for the two. For example, for general relativity, space-time is flexible, dynamic, and it is a physical object, while for quantum physics, it's static, rigid, invariable, a sort of substance, matter, within which physical objects come to be. So there are 2 representations of space and time which are completely different. So the challenge for theoretical physicists is to define a description of space-time which makes it possible for them to describe all the 2 together or the 4 forces together, taking into consideration what is said by general relativity and quantum physics. There are several possibilities or avenues that are being explored. One, which is called the superstring theory, the other one, which is called non-commutative geometries, twisters, and also I'm not going to describe them all because there's also the new gravitation theory, but I'm just going to give you 2 or 3 examples, but I really can't explain it. The first, which is studied most, is that you study the so-called superstring theory. That is Gabriele Veneziano, that you're very well acquainted with, who is a professor in Paris at the Collège de France, has greatly contributed to the development of this theory. He is even considered the founding father of the superstrings. And the idea which has been developed is that if one could look at an elementary particle such as electron or neutrino or quarks with a very powerful magnifying glass, one would not see an object, a point like what you would see a string, a sort of little tiny string with 2 ends or a loop, and these develop in a space-time which has not 4 dimensions but 10 dimensions. The idea is that there are some dimension of space which are greater than the ones we know, which are folded on themselves in very small distances, so that these dimensions are imperceptible. But for physicists, that developed the string theory, these dimensions exist, but they simply can't be seen. And this theory of strings enables, it still has to be proved, to describe the 4 forces at the same time. Simply, this theory predicts something which is very important. That is to say that the temperature in the universe, if the theory is correct, presuming it is, cannot not to the infinite. That is to say, at all moments in its history and at all places in its time, it is necessarily below a certain threshold, which is very, very big but not infinite. So what I said earlier on is that the initial singularity, which we associate the Big Bang to, corresponds to an infinitely high temperature and density and to a 0 volume. And according to the string theory, this is not possible. It cannot exist because there are no infinite temperatures in the universe. And therefore, why should we replace, how should we replace this? Well, here you can see it. This is the normal Big Bang theory with variations. There's nothing, there's no space, and then suddenly the universe appears with time, space, and energy. But according to Gabriele, if you take into consideration the superstring theory, you must replace this initial singularity, which we associate with instant 0 Big Bang, with a transition between the universe of before, which was contracting, and because its temperature increased, its density increased until it reached the maximum temperature as explained by the string theory. Once the temperature was reached, it could not contract itself more because that was impossible. You can't increase its temperature even more. So before it reached a 0 point, the universe folded on itself and became the universe in expansion, which is our universe, or the universe as we know it. So you see that the questions that we had in the 50s, what existed before the Big Bang, St. Augustine's question, what did God do before creating the universe, or what type of, well, what started the Big Bang? All these questions in this framework are not raised in the same manner, since the question of knowing what happened before the Big Bang is a question of physics and no longer a question which is related to metaphysics. And therefore, the conclusion that we reach is that in that interpretation, the Big Bang can no longer be considered as the origin of the universe, but simply In fact, it is a phase of the universe. I had said that the superstring theory had not been proved experimentally. Some physicists think it's the good theory. Others criticize it, saying, for instance, you introduce additional dimensions without proving that they exist. So nobody can really guarantee that the principles underlying this theory are correct, and thus the conclusions which I have retained there can be criticized in saying the hypotheses that you started with are unverified. But what is interesting is that other physicists have tried to describe what happened before Planck's wall, starting from a completely different hypothesis. These are physicists that considered that space-time was not continuous and flat, but a series of space-time areas, which means that a volume in space is necessarily a multiple of an elementary volume, which is very, very small, but is not zero. Otherwise said, in the space, there cannot be volumes of whatever size. All are multiples, whole multiples of an elementary volume, which is linked to Planck's constant, which is the fundamental constant of quantum mechanics. It simply says that the space-time is granular. That is to say, small grains as if they were atoms of the space-time. And this is the theory. What is interesting is that when you apply this theory to the description of what happened before Planck's wall, you reach the same conclusion. That is to say that the universe contracted until it reaches the smallest possible volume, which is not zero, and at that point the universe flexed on itself and became the expanding universe that we know. And what is interesting is that there again the idea of origin has disappeared. That is to say that what existed before the Big Bang is not the nothing. It is a dynamic process, the Big Bang being a moment of it and not being the initial singularity which we spoke about in the 50s. And the interesting lesson is that if we look at the other cosmological models that have been developed by other physicists, for example, those say is a fluctuation, a quantum fluctuation, or that it started with a collision between what we call brands, that is to say, four-dimensional structures. In all cases, the Big Bang is reinterpreted not as the origin of the universe, but as a moment within the history of the universe, which means that the issue of origin is an open question. What I call the origin of the universe is the origin in the essential sense of the word. That is to say, I suppose that there is a nothing, and that then suddenly there is a first thing that appears. That is what I call the origin of the universe. If you say that at the origin of the universe there was already something, then I would ask you, where does that come from? And thus, the question of the origin will be shifted. And you will have to deal with a question which will be asked an infinite number of times. And if you tell me that the thing that is at the beginning of the universe is always there, it means that the universe did not have an origin. There has always been something. Thus, what I call the origin of the universe is the transition between the absence of all things and the appearance of the first thing. And we do not know if that transition has or has not appeared. We have not been able to scientifically prove that the universe had an origin, nor have we been able to give a scientific demonstration that it did not happen that way. So maybe the universe had an origin, and maybe it didn't have an origin. It's an open, there hasn't been an answer to it yet. And the issue which I would like to conclude my presentation on before leaving you the floor for questions is the following. All I have said so far is something I have said on the basis of the laws of physics. I spoke about general relativity, I spoke about the superstrings, which are what we define formalism, that is to say, a series of equations that make it possible to describe the events or in physics. And to talk about that, I had to refer to the laws of physics, which are present in this theory. But if we were to consider that the universe really had an origin, would one consider that the law of physics had already been determined at such time? In other words, did they have a legal framework which had already been fixed? Or are the laws of physics something that appeared in the course of the history of the universe? This question is a metaphysical question which Plato had already discussed, and it is an issue which no one knows how to answer. Nobody is able to answer such question. While to say it in a more practical sense, I'm going to suggest that the universe had an origin. That is to say, there was a nothing, and then suddenly the universe appeared. And with that, we had the first particles appearing. And there was a moment when, for example, the first two electrons appeared. As you know, the electrons have a negative electric charge, and therefore they repel each other with the electromagnetic force. Now, if I say this, it's because I'm at school, like you. And at school, we learned that two electric charges with the same sign repel each other. But the electrons forgot to go to school. And so how do they know that they have to repel each other? Do they obey orders? Does the electrostatic law, written into its structure, is it written into the laws of the universe, or is in a part of participated democracy, they have negotiated with the universe, asking, well, which law of physics should they adopt? Should they, for example, attract each other, repel each other? What should they do? Well, no one is able to answer these questions. Otherwise said, we are unable to say whether the laws of physics are part of the universe, or whether the laws existed before the universe. If they're part of the universe, it means they're immanent. If they're outside the universe, they're transcendent. And these are fundamental questions. And I'm really sorry that people don't ask these questions more insistently. For example, you may have read Stephen Hawking's latest book. He's a well-known astrophysicist, and in his latest book, on the last page of his work, which talks about the theory of superstrings, he says the universe didn't need God to be created. The laws of gravitation were enough. And he explains that the law of gravitation acting on the nothing engendered or created the universe and all the things that exist within. But you see that this is a rather naive formulation, because if you define God as the being that created the universe, then you must say that, if necessary, the laws of gravity are God, or God is the law of gravity, because they are the ones that created or engendered the universe. If God is the laws of gravity, when you fall down the stairs, because of gravity, in fact, you are a sort of, you're praying, in other words, or it's a gracious, or grace has to do with it and God. So the question is whether one day we will be able, on the basis of the laws of physics, to describe the origin of the universe, because to describe it, you must suppose or presume some laws of physics that exist at the moment of the creation. So in implicitly means that the laws of physics pre-existed, and that raises the question as what is at the beginning or the origin or underlies the laws of physics. And this means that we are caught in a sort of regression or backward movement, and I think that the question of the origin of the universe, it is possibly not so much of an enigma or a problem, it's possibly a mystery. That is to say, a question that we will never be able to solve. This does not mean that we are not able to identify the origin of many things in the universe. For instance, you have heard, last July, you heard of the discovery that they made in CERN in Geneva of a new particle, which is called Higgs boson. Well, this particle answers a question, the discovery of it corresponds to a question which is not referred to the origin of the universe, but the origin of the mass of particles, because our equations, the ones which make it possible to describe the interactions between and among particles, which come from the Standard Model, in the 1960s, suggested that elementary particles had no mass. Equations said electron had no mass, quark had no mass, neutrinos had no mass, but when you measured them, you saw that clearly they had a mass, which was not nil. So there was an inconsistency or a contradiction between what the equation said and the measurements that they could make. So when there is such an inconsistency, normally you say that it's the equations that are wrong, the measurements are right. And it is thus that most physicists reacted. But a small number of physicists, including the one called Peter Higgs, said that maybe the equations were right. Maybe elementary particles have no mass, but we physicists are mistaken and have been mistaken since Newton on what a mass means. Instead of considering that a mass of a particle is an inherent feature, a property which is therefore of the particle, why not imagine that it is a secondary property or characteristics which derives from the interaction between particles without a mass with a void, which means that there is something in the vacuum. With the Higgs boson, they go into collision, and it is by colliding that they slow down and gives them what we could now term an apparent mass. This idea was published in 1964, and it took 48 years, and the building to the collider, which cost several billion euros, the contributions of millions of physicists and engineers for decades, and a lot of Italian ones too, to reach this discovery, which will certainly be recognized by the 2013 Nobel Prize. We have understood the origin of the mass of particles. To understand such origin, you had to develop or understand another physical entity which preceded the mass, which means that the Higgs field with the Higgs particles then understood. In other words, in physics, we now explain the appearance of a physical entity through another physical entity. And to say it in more philosophical terms, we explain the being through a being. And to explain the origin of the universe, we would therefore be able to say, what is the being that preceded the universe, which the universe is the product of? And you see that that is a very difficult question, and I'm not really sure that there will be an answer, a scientific answer to that question. And that is why I say that the question of the origin is a real mystery, and one has to beware of those who say that they have solved the problem of the origin of the universe. Thank you very much for your attention. Thank you very much.